Good afternoon, selected audience, and welcome to this exciting event, which is the first Kepler lecture of 2025. Kepler lecture series is organized by the Center of Excellence Center for Planet Habitability, which is part of the Department of Geosciences. And today I'm very happy to introduce the Kepler speaker, who is a rising star in geobiology coming from University of Bergen, Desiree Roerdink, Associate Professor at University of Bergen. Desiree is originally from the Netherlands, and she got a master's degree from there and a PhD, cum laude. But very quickly after that, she came to Norway. I think you spent the last 11 years in Norway, first as a postdoctoral fellow with the Center for Geobiology. And since 2016, she's an associate professor with that center and Center for Deep Sea Research. And she describes herself as an isotope geochemist with a passion for the early Earth, deep sea minerals, and mass spectroscopy. And she's keen to transfer knowledge to students through new teaching methods and to enthuse the general public about science. She's personally driven to make academia a more inclusive and diverse workplace, which I think it's a wonderful task for your academic career. Well, Desiree, she is working with both very young environments on Earth, which are mid-ocean ridges, but also the very old, the Archean, and she will talk about these very old environments on Earth. And I'm super curious to see what she will share with us. Desiree, the floor is yours.
Okay. Thank you very much, Carmen. Is it working? Yes. Okay. Yeah, and thanks for inviting me to give this talk. So I am going to take you all back to the beginning of Earth history today, to the period called the early Archean. And I think this is the most fascinating period we can study in Earth history. And the reason for that is very nicely shown, I think, on this famous photograph from the Apollo 8 mission. Because it shows that we live on a planet that's definitely not dead. This life that we know today, this originated, or this started at the beginning of Earth's history in the early Archean, or maybe even before. And as far as we know today, we are the only ones that have this life. Of course, this is all up to you guys to figure out if that's true, but at least this is our current status. And of course, the question then on how this life originated, this is one of the biggest science questions that we haven't solved, and many people from different fields working on this. And for me as a geologist, what I can contribute to that is to think about where this life might have started. And you know, there's different places that have been suggested, you know, seafloor hydrothermal vents. This is actually a vent in the Norwegian Sea. Places with a lot of chemical energy for life. Maybe shallow marine environments. This is a place in Australia. Maybe this could be, you know, sunlight was available. Or maybe hot springs on land. This is actually something that sort of more recently has become a bit of a thing, with people starting to realize land might have appeared earlier than we thought. So maybe a place like this, like Geyser on Greenland, on Iceland, maybe that was a place where life could have started. Okay, so how can we find out? Well, this is directly sort of the complication of studying these early environments, because our rock record is very limited, if not absent, basically, from this period of Earth's history. So this is a timeline from the beginning of Earth to today, and the period that we're talking about, let's see, we don't have a pointer, right? Something. The period that we're talking about is sort of the pinkish colored period here. And from this time, there are extremely limited rocks. So the, yeah.
It's better to just point with your clicker.
Okay. Yes, okay, I do that. Okay, tack. So the, oops, there we go. So the closest answer we can probably get lies in the early Archean rock record, because before that, we have extremely limited rocks available. So we're talking about the period here from roughly 3.8 to 3.2 billion years ago. Now, there are older rocks than that, but I'm just going to go quickly through that and show you that they're kind of useless for figuring out what the early environment looked like. So the oldest material that we actually have on Earth are zircons from a place in Australia called Jack Hills, and these have been dated up to 4.4 billion years old. And you know, the good thing about zircons is that they are very robust time capsules, so we can date them, they record information in some isotope geochemistry, and people have tried to extract information about that, about the early environment. But the thing with zircons is that they crystallize from a magma, so they're not a direct product of the early environment, and we can only get indirect evidence about the early environments from them. Okay, so not so great for these environmental reconstructions. The same is true about the oldest rock that we have on Earth, which is the Acasta gneiss in Canada, just over 4 billion years old. And you know, okay, this is great. It's the oldest piece of crust that we have preserved. But again, the problem with this rock is that it has a crustal origin. It's a magmatic rock. So basically, you cannot really extract information about the surface environment from this. And even if it would be, it's also a highly metamorphosed rock. So basically, any signals have been erased from this time. Things get a little bit better when we move slightly younger to a place called Ishua in Greenland, because here we have what we think is the oldest sedimentary rock on Earth. So now, now we're getting better. At least now we're getting into rocks that formed at the actual surface of our planet. So great for environmental reconstructions. However, this rock is actually still controversial in its origin. People are actually arguing if this is sedimentary or not, which is the case with many of these rocks from Greenland. Are they actually sedimentary rocks, or are they actually metamorphosed? And in addition to that controversial origin, all the rocks in this place are highly metamorphosed. So basically, again, if there's any signals from early environments or early life, then they've basically been cooked out and very difficult to extract information from them. So, okay, this sounds kind of hopeless then, because what can we then do? Now, the topic of my talk today is about a mineral that is going to solve many problems that we have with these other rocks, and that is the mineral barite. So basically, the next half hour-ish is going to be a bit of a sort of declaration of love to barite, because this is a mineral that has great properties, and it found at the right time in Earth's history to extract a lot of information about early environments from it. So let's take a look at Archean barite. So here we have our time overview again. And the Archean barites are found between the period of 3.52 and 3.2 billion years ago. So, okay, we're not all the way back at Earth's history, but we're still pretty early in Earth's geological history. And we find them in 3 different places on Earth: in South Africa, in Australia, and in India. And why is this barite such a great mineral to study? Well, first of all, it's a mineral that we know from the geological settings where we find them, it was formed at the surface of the Earth. So similar to the sedimentary rocks at Ishua, the barite is also a surface rock, so this can record surface conditions at this time. What's also great about barite is that it's very insoluble. It's actually one of the most insoluble minerals that we have. So yes, that makes it actually a pain to work with it in the lab. It doesn't really dissolve in acid. But it also means that it's very robust against metamorphism, against fluid alterations. It basically, once it's formed, its chemistry stays as it was in the beginning. So we don't really have to worry so much about metamorphism. Also barite, so barite is barium sulfate, and that means that it contains an element that is also biologically relevant. It contains sulfur in its oxidized form. So if we want to think about places where early life was maybe present in these environments, then it's very nice to have a mineral that actually includes an element that was probably used by early life. And not only is there oxidized sulfur in these sulfates, many of these barite deposits, they also co-occur with sulfides, with the mineral pyrite, which is sulfur in its reduced form. So this means that basically we have a redox couple trapped in the rock record. And this is great for studying early redox processes in the environments and biological processes. And lastly, for people like me, I'm an isotope geochemist, sort of by training. Barite contains very useful elements. Sulfur, strontium, and just behind the plant is oxygen. And these are all elements that we can measure isotopes on. And that makes people like me really excited because it means that we can use this to try and, again, extract information about early redox processes, early environments. So yeah, barite is a great mineral to study. So this is what I'm going to talk about for the next half hour. So just, that you know. Let's take a look first at what these barites actually look like, to give you some sort of context before we go on and extract all kinds of chemical information out of them. So first of all, as I said, we have these barite deposits in 3 locations, in India, South Africa, and Australia. So these are 3 different cratons, the Pilbara craton, the Capvel craton, and the Darwa craton. And they are all confined to here we are. To this period, the Paleoarchean, it's actually quite remarkable. They completely disappear in the Mesoarchean. That's another big question that I'm not going to touch upon today, but it is kind of odd that they disappear. But at least we have in the Paleoarchean, so the time when a lot of things happened on Earth, we have quite a good coverage of barite deposits covering this whole period of about 400 million years. So what do these barites look like then? And also just to give you an idea of what this is like in the field. This is one of the 2 barite deposits that has probably been most studied, the place called North Pole in Western Australia, a barite that's almost 3.5 billion years old. And here you can see on the left side an image, there, where we have, okay, where is the mouse gone? There, where we have altered mafic volcanics, so this has been strongly hydrothermally altered, and on top of that we have bedded barites. Here you can see thin, sort of 10 centimeter-ish thick beds of barites, and this occurs over quite a large area, several tens of meters. On the right side you see another way of this barite forming. This is a barite vein cross-cutting through blocks of chert, so strongly silicified rocks. And so this is barite that we find in a setting with volcanics, but we also have barites in the rock record that are found in settings with sedimentary rocks. This is the other barite that has been most studied to date, and this is in South Africa, barite valleys. It's a bit younger, about 250 million years younger. And also here we find bedded barite. Here on the left you can see these are thin beds of beautifully bladed big crystals of barite. And then overlain by chert and jasperite, so more iron-rich chert. And here on the right side, we also have some really funky shapes of barite that we don't really understand actually why this is. They have been called in the past in literature cauliflower barite, so they actually look like a big cauliflower, and we don't really know why barite grows that way. But it's something we see in more places, and again, it's very strongly associated with chert, so with amorphous silica deposits. And this is the thing we see for all the barite deposits that we go to in the field. Okay, so that just gives you an idea of what these barites look like. But again, before we go do all geochemistry on it, we should know a little bit more about what kind of environment they actually formed. And for this, we took a look at the chemistry of the cherts, because as I said, they're so strongly associated with it. So for example, we see cherts that are associated with the barite, that they are very strongly enriched in barium. This kind of makes sense because you need a supply of barium to form these barium sulfate minerals. So this led us to the idea that these fluids that precipitate this amorphous silica have also brought in barium into the system. And also when we look at the rare earth element composition of the barites, here on the right side, then you can see that these colored lines, these are from the cherts, and they're sort of in between what you would expect for a high-temperature hydrothermal fluid and what you would expect for seawater. So this europium anomaly, this peak, this is what you typically get in a high-temperature hydrothermal fluid. And we see it in some, but it's not super convincing in all of them. And at the same time, the light rare earth element depletion, so the slope of this curve, is something we also sort of see back in many of these charts. But it seems to be some sort of bit of both. So this is what leads us to think that, well, these barites formed in some sort of setting where we both had seawater and hydrothermal activity being important. And this is something that more recently we followed up with some other geochemical studies. So we measured silicon isotopes in the cherts, and okay, this again is perhaps a bit more complex story than the way I present it here, and there's a bit preliminary interpretations, but what we see in the silicon isotopes in these cherts seems to match with with what I just told about this seawater influence. And the way that you can see that is this plot shows sort of estimated, say, n-member compositions of Archean seawater. So this has a positive silicon isotope composition, and our hydrothermal fluids have a more negative composition. And that's largely based on sort of extrapolation from what we see today and also measurements from really hydrothermal settings in the Archean. And if we look at then the cherts that we measured, or the cherts found and associated with the barite, then we see that they're kind of heavy in silicon isotope ratios. They have relatively high ratios, which seems to be consistent, again, with this seawater, with a fluid that at least had a strong seawater signature to it. Something else that I've just been fairly recently working on is then oxygen isotopes. And this also confirms this sort of system where we don't have very high temperature hydrothermal activity, but it seems to be slightly hotter than just seawater. And without going in all the full details of this plot, basically what it shows is these colored lines that you see here. These represent sulfate, the composition of sulfate in equilibrium with water at different temperatures. And these colored plot dots here, this is the barite, and you can see that sort of the temperature range that these barites seem to indicate is, well, say roughly between 50 and 150 degrees. So we're, depending on where we agree on the temperature of Archean seawater, which could have been a complete talk in itself, but it seems to be hotter than sort of background seawater. So this leads us to this idea, this model that these Archean barites formed in basically low-temperature marine hydrothermal settings. So they're not completely marine, they're not completely sedimentary, they have a hydrothermal influence, with, for example, barium coming up through faults and then reacting with seawater and precipitating out as barites. And this is actually also consistent with other field observations. We don't find any massive sulfides, we don't find very clear volcanics and everything associated, or volcanic dikes or this sort of stuff associated with these barites. So everything seems to sort of make sense with each other. So that means that these barites are really kind of like a great time capsule to go back and look at these early marine hydrothermal settings. They are a place where life could have lived, and they are so they're basically the right rocks, the right place, well preserved. So a great mineral to study. So let's take a look then at what we have learned from this barite. So first of all, okay, this is a very sort of simplified cartoon. I'm going to show this several times. I should just put a little disclaimer because it shows a subduction zone, which, okay, we don't actually know if this is happening, but I made this a long time ago. So subduction or not, but the early Earth was basically a system where we know we had output of volcanic activity, putting volcanic gases in the atmosphere. We know we had an ocean. We know we had hydrothermal circulation. And thanks to barite, we also know that we had chemical reactions happening in the atmosphere. And this is a process called atmospheric photolysis. So how do we know this from barite? Well, we have to go to one of the main elements in barite, sulfur, and look at its sulfur isotopic composition. So let me just go back to the basics for a second so we're all on the same page. Sulfur has 4 stable isotopes, and 32 sulfur is the most abundant one. Almost 95% of all sulfur on Earth is 32 sulfur. And so normally when people measure stable sulfur isotopes, we would measure this ratio of 34 over 32 sulfur. We indicate that with this delta value. This is basically a normalized ratio. And this is often, that's often enough. This gives us a lot of information about biological reactions and stuff. But luckily, somebody about 20 years ago, 25 years ago already, decided to also measure the minor isotope of sulfur in Archean rocks. And this is the 33 sulfur. So you can see its natural abundance is much lower, and this is why people actually typically didn't bother measuring it, because it's much harder to do from an analytical point of view. And in principle, fractionation of sulfur isotopes, so changes in isotope ratios, they are predictable. This is what we call mass-dependent isotope fractionation. So this equation is something that basically meant that you wouldn't have to measure this more difficult ratio because you could just calculate it from the easier measurable ratio. However, what James Farquhar and colleagues found in around 2000, is that there are apparently processes that produce a correlation between these 2 isotope ratios that does not match with that number, with 0.515. And this is what was then called mass-independent isotope fractionation. It's actually a bit of a wrong name because it still has a mass dependency, but it doesn't have this mass dependency. And so they measured this minor isotope ratio in Archean rocks, and then decided on that we indicate that with this symbol capital delta 33S, which is basically the measured value of our minor isotope ratio minus with what we predict, or what we expect from this mass dependency. And what was found was quite striking, because basically all the rocks older than about 2.4 billion years ago, this is the time when oxygen started to appear in the atmosphere, all the rocks older than that show this mass-independent sulfur isotope signature. And this was then interpreted to reflect atmospheric reactions in a low oxygen atmosphere. Actually, this is, isotopes are very often not providing any smoking gun type of evidence, but this is probably one of the few times that it actually does, because it is really not possible to explain this presence of mass-independent fractionation in any other way. So these atmospheric reactions, this is what this atmospheric photolysis is, and basically the way this works is that you have volcanic SO2 that reacts with UV radiation. If there's no oxygen, there's no ozone layer, so UV radiation comes down into the troposphere. And then this SO2 is basically broken down into elemental sulfur and sulfate. So how is barite involved in this then? Well, only one of these 2 photolysis products is preserved in the Archean rock record. So we have elemental sulfur that is produced, but that's not preserved. We don't find any elemental sulfur back in Archean rocks. But sulfate, well, I already started, declaring my love about barite. Sulfate is there. We have sulfate preserved in the rock record. So this means that we can use the isotopic composition of this sulfate to constrain what kind of atmospheric reactions we actually had. So let's take a look at this figure that I showed earlier, but now indicated which ones are the sulfides and the sulfates. So in blue is the sulfide minerals. We'll get back to that in a little while. And in orange are the barite, the composition of the barite. And so you can see that this predicts that whatever atmospheric reaction was happening, it must produce sulfate with a negative Kep delta 33 signature, so negative mass-independent fractionation. And this is then input that we, as geochemists, can basically give to modelers who are modeling or trying in the lab to experimentally constrain this reaction, this photolysis reaction. So this figure here basically shows all kinds of different pathways that people have suggested. So on the x-axis, or on the y-axis, we have the Kep 33, and here we have delta 34s. And then in orange is the measured composition of the barite. And so you can see that some of these reactions are not consistent with the composition of the barite. So basically, this is UV photolysis at a wavelength of 193 nanometers, et cetera, This is basically decided by what kind of laser people have in the lab. This is why they're a little bit arbitrary, these wavelengths. But what you can see, for example, is that this reaction that was proposed is supposed to produce sulfate with a positive Kep-Del 33 signature. So that's not working with the rock record. And so in that way, the barite provides basically clues about which atmospheric reactions maybe work in the lab or in your model, but don't work with the rock record, which is our ultimate, that's what stuff needs to match with, right? Because that's what we actually have. So for example, this reaction, the red one, producing sulfate with a very negative delta 34s signature, well, that's not going to work with the composition that we see. This one is also not going to work because it's supposed to produce sulfate with a positive signature, and with a positive Kep-Del 33 signature, and the same with the chain formation, as I just pointed out. So even though there's still many options, of course, in this again, slightly simplified plot that are still possible, it does provide important constraints that we cannot get from anything else, because elemental sulfur we don't have, and any pyrite that we measure has been going through a reaction to go from either elemental sulfur or sulfate to sulfide. I should just sort of add here a little disclaimer that we still haven't really solved this. So there is still a very consistent mismatch between what people have produced in the lab versus what we measure in the rock record. So this is definitely something that, hopefully the next 10 years or so we can figure out and put some better constraints on the composition of the atmosphere in which these reactions took place. Okay, so that's the atmosphere. Barite also produces constraints or captures basically weathering inputs into the earliest oceans. And this works because of another element that is present in barite, not as a major element, but as a trace element or minor element, and that is strontium. So the way that this works is that we know this from the modern record, where people have used carbonates, for example. Chemical weathering of felsic crust, this can be traced in chemical sediments, so in sediments that precipitate out of seawater. And the reason for that is that basically the strontium isotopic composition of the continental crust is very different from the strontium isotope ratios in the oceanic crust. So basically, if you weather material from continents, this produces a different strontium isotopic fingerprint in seawater, which can then be captured in chemical sediments forming out of the seawater, compared to if you would just have hydrothermal activity, for example, in providing strontium. And so strontium, barite, again, is a fantastic mineral for this, because strontium, if you look on the left side, you can see the ionic radii of strontium, barium, and rubidium. So the strontium system, this isotope ratio, strontium is formed by decay of rubidium. And so normally over time, if you just have an igneous rock, you have rubidium and strontium present, and the strontium isotope ratio will change over time because of decay of rubidium. So this means that if you take a modern-day strontium isotope value, you need to back-calculate what the original value was 3 billion years ago. But with barite, we don't have to do that, because rubidium really does not fit into the crystal structure of barite. Strontium does, because it's similar in size to barium, but rubidium does not substitute for barium. So this means that basically, if we have barite that formed at a certain time in Earth's history, that the present-day strontium isotope ratio is exactly the same as the strontium isotope ratio at the time the barite formed. We don't need to do all kinds of complicated corrections, and we can basically just measure today's strontium isotope ratio to figure out about the fluid that the barite formed from. And in contrast to, for example, the carbonates that I talked about, barite's much more robust than carbonate, so it's much better preserved. So with this in mind, we measured strontium isotope ratios in all these barites that I showed you earlier, so these 7 different deposits. And what was quite striking is that the strontium isotope composition of these barites was much higher than what you would expect if the strontium had just come out of the mantle. So just out of hydrothermal ocean seafloor alteration. And this was different from what people always thought, because until basically a few years ago, it was thought that land, or that seawater would have a composition similar to the mantle until about 3 billion or maybe even 2.5 billion years ago, with implications for weathering inputs. But what these barites show is that that seems to be wrong, because the only way to explain these higher strontium isotope ratios than what we see in what we predict from the mantle curve is that material from continental crust, remember this had a higher strontium isotope ratio, was somehow put into the earliest oceans from which these barites formed. So this means that in the earliest Archean, we may not have had a lot of land, but whatever land was there, or whatever felsic crust was somehow exposed to the air, it was weathering so intensely that it is recorded in seawater at this time. And then, we did since we have a lot of barites and they somehow beautifully plotted onto sort of one array, we extrapolated this and said, okay, well, the moment that this seawater curve starts to deviate from the mantle curve, this must be roughly the time at which weathering started, or at least at which weathering started to significantly change the chemistry of the earliest oceans. Okay, so then again, well, that's great, weathering, fine that you constrained the onset, but what does that matter for early environments and for early life? Well, weathering is really important for biogeochemical cycles, because not only does it, as we know from today, take up CO2, it also produces or puts nutrients into the oceans. For example, phosphate is always one that is sort of very popular with Archean geochemists to mention, but it is a critical nutrient for life. Having this flux starting as early as around 3.6, 3.7 billion years ago means that life at least could be fueled by these nutrients coming from early land. And so, if you look at the evidence that we have for life in the rock record, some of these are definitely disputed, but they all kind of point back to this time in the Archean. Where has the mouse one here? In this time in the Archean, that sort of around 3.5 or maybe earlier than that. So this is, of course, a bit of arm waving, geology, but perhaps that is not a coincidence if you think about when the supply of nutrients may have started. Okay, so that's ocean composition and weathering, another great thing that barite has been very useful for. The last thing I want to talk about is the actual biological cycling of in the environments that the barite represents, because you see here a small figure that says the oldest sulfur isotope evidence for life, and this actually comes from a barite deposit. So barites also really good at capturing sulfur cycling. Remember that I talked about that barite contains oxidized sulfur and often co-occurs with sulfide, and this provides us with fantastic time capsules to look at these early sulfur cycling. So let's take a look at this microbial activity and the sulfur cycling then. So okay, this is, I basically just said this, that barite, the barite that we have, the Archean barites, all deposits except for one, we find fine-grained pyrite crystals. So pyrite is iron sulfide, so this captures the reduced form of sulfur, whereas barite captures the oxidized form of sulfur. And this is a great combination again, because we know from modern Earth that life uses this redox coupling to extract energy. And so it's a logical pair to look at also back early in Earth's history. So if we look at the sulfur isotope ratios, again, back to sulfur now, of barite and its coexisting sulfides. So this is a plot showing just delta 34S. So this is just this mass-dependent fractionation. We have in orange the barite, and in blue the coexisting sulfide minerals. And what you can see is that there's quite a shift if you go from the sulfate to the sulfide. And this is what, for example, this evidence that I just showed, all this evidence for sulfate reduction, is based on. This shift is very typical for a process called microbial sulfate reduction, so sulfate being microbially transformed into sulfide. This is a process we still have in the modern-day oceans, hydrothermal systems, deep-sea sediments, shallow shelf sediments. This is a process that's very common. And in today's settings, we find very large changes in isotope ratios between sulfate and sulfide, up to like 70 per mil or something. In the Archean, this was less, because basically the magnitude of this isotope effect correlates with seawater concentrations of sulfate, and this was quite low in the Archean. But what is great about this photolysis reaction that I talked about earlier is that we can actually use these minor isotope ratios in barite to constrain what type of metabolisms we had. So microbial sulfate reduction is only one type of microbial sulfur cycling we might have had in the Archean. There's also this elemental sulfur that was produced in the atmosphere, and microbes are also capable of doing something with that, whether it's either reduction or disproportionation or other kinds of things. So we can use this cap delta 33 value that was produced in the atmosphere to differentiate between whether it was sulfate that was being transformed into pyrite or whether it's elemental sulfur transformed into pyrite. And the reason for that being that any pyrite formed from elemental sulfur will have a positive cap 33 signature, and any sulfide produced from sulfate will have a negative signature. Okay, so keep that in mind. Let's have a look at some real data then. So this is a drill core that I worked on in my PhD project. It's a drill core from South Africa, from one of these barite deposits that I showed you pictures of. And we see a very big difference when we go from the barite-rich parts of the core to the barite-free parts of the core. So on the left side, you can see the sulfur isotope ratios in gray, the sulfur isotope compositions in gray of sulfide in the barite-rich parts. And if we go to the barite-free parts, we see very different values. So this suggests that something is happening environment-wise when you go from barite-rich periods to barite-free periods. And this is actually something we don't just see in this drill core. We actually see it when we look at compilations from, for example, all the old rocks in South Africa, whatever data is there, when we compare what we have in the barite, so when we have sulfate around versus when we have, no or less sulfate around. I mean, with even not knowing anything about sulfur isotopes, I hope you can agree that there's very distinct signatures here. Even if we look at global records, so on the left side we have barite, here we have BIFs and cherts, banded iron formations and cherts, and here we have carbonates. And even here you can again see that we don't really observe this big shift, for example, in the BIFs and the cherts. a little bit in the carbonates, but actually not until the Neo-Archean. So when we go the end of the Archean period, so much younger than when we are at the early Archean. So this suggests that basically these barites represent some kind of special environment. And the way that we interpret this is that in the settings with barite, you basically, this is basically where sulfate reducers were happy, sort of to put it the simple way. So this isotope effect that I was talking about, that we see in modern settings, this is only sort of visible if there is enough sulfate around. If there's too little sulfate, then basically the microbes just use whatever they have, and there is no sulfur isotope fractionation expressed. So what we think is that when there is barite around, there is somehow an increase in sulfate concentration locally, and this is where sulfate reducers then basically flourish in the environment. Whereas in times when there is no sulfate being deposited, it seems that this mechanism, it either disappears or it just doesn't show up in the rock record because we don't exceed this threshold for expressing isotope effects. But what we do see is that in those periods of times, sulfide reduction, elemental sulfur processing seems to become much more important. So it seems like we go some sort of shift from sulfate-rich with different implications for the life living there. So sulfate-rich, sulfate reduction, sulfate-poor, switch over to a different mechanism, different metabolism. So, then we sort of think about these barite. This talk was about time capsules for early Earth environments. So, what I think that this barite shows is that we have some sort of setting where, well, I like to call it a marine sulfate oasis. This was a time, where these barites represent places where sulfate was somehow more present than perhaps somewhere else. This also puts a little sort of warning on that maybe we shouldn't extrapolate the data we get from these barites to the whole Archean rock record, which we typically love to do. But there seem to be special places, special environments where life was actually thriving, where we have sulfate reducers happily living and maybe fueled by inputs by weathering in terms of nutrients, definitely fed by sulfate coming from this atmospheric photolysis process. And then hydrothermal activity, well, maybe these were hyperthermophiles, for example. We know from phylogeny that the oldest sulfate reducers in the rock record are hyperthermophilic or thermophilic, so microbes that like to live at relatively high temperatures. So then, good timing. So I hope I have convinced you with that the Archean barite really represents a critical part of the rock record to reconstruct early surface environments. It's basically this unique combination of a very robust mineral that is not affected by weathering, it's not affected by metamorphism. It contains all the useful elements to do these geobiological studies on. It contains elements that are important for life. So if you want to look at places where life lived, then this is a really good place to go to. And also, it covers this really important time in Earth's history, between 3.5, 3.2 billion years ago, when we know, or at least we think we know, that a lot of things happened to Earth. Plate tectonics might have started. We start to see more and more evidence for life around this time. So this is really when things happened. And the barite covers exactly that period. Okay, what have we seen from what I presented today? We have some low-temperature hydrothermal systems. Not everything was a black smoker on the early Earth. The barites definitely were not a setting like that. They provide important evidence for this anoxic atmosphere with this photolysis product that produced sulfate from the atmosphere, with this MIF signature that we talked about. We had seawater chemistry that was already influenced by crustal weathering already from the very early Archean. 3.6, 3.7 billion years ago, it seems that seawater started to be chemically affected by what was coming from land. Also, these barites seem to have provided good places for sulfate reducers to live in these, well, let's call them marine sulfate oases, so places where maybe sulfate was locally enriched, but providing a habitat for early life. And then outside of them, a very different type of setting, which again makes you think about, in terms of extrapolating data from these barites, that perhaps we should be a bit careful with that. But we've seen evidence for elemental sulfur cycling outside of them. So, okay, the barite is probably not going to solve the question on where life exactly started on Earth, but at least it gives us really important clues about where early life lived. And so maybe this is as close as we can get to actually answering this question, or at least put constraints on the type of settings we need to think about when we think about origin of life. And then with that, I would like to thank, I could not have done all this work without this great team of people that I've been doing most of this work with, Mark van Zuilen, Dylan Wilmeth, and Paul Mason. And then there's a heap of other people that have contributed to the data that I presented. Thanks.
Desiree, thank you so much for such an exciting presentation. Very well argumented, for me at least. Thank you, and this barite is indeed a lovable thing.
I'm glad I convinced you.
All right. We would like to take some questions from the audience. Matt?
Thanks, that was a very interesting talk. I was curious if the sulfate reduction could occur in the absence of microbes. Do you necessarily have to have microbes present in order to explain those isotope ratios, or can the reduction process occur abiotically?
Yes, that's a very good question. Thank you for asking that, because I did kind of skip over that. Yes, you are absolutely right. So sulfate reduction can occur abiotically, and it does, for example, occur in modern-day hydrothermal systems in the subsurface. But you need high enough temperatures for that. So you need temperatures above 250 degrees, because what life does is speed up kinetics, but abiotically, this is a much slower process. So, we don't really find evidence for these high temperatures, because if you are at if you are 250, 300 degrees, then you would expect to see kind of more like these black smoker settings that we have on the modern Earth. So you would expect to mobilize metals, much more metals then as well, and get massive sulfide deposits, for example, associated with it. And we don't see this with these barites. People have also looked, so this is one argument, sort of comes from field observations, that this is unlikely. The other argument comes from the minor sulfur isotopes. So microbial sulfate reduction produces a very specific shift in the minor sulfur isotopes. You need very high precision data to look at that, but people have tried to do this, and they see shifts consistent with a microbial process and inconsistent with an abiotic process. So it seems that everything sort of points at that it's very unlikely that this is an abiotic sulfate reduction. Yeah, but thanks. Good question.
Maybe I misunderstood something, but so your barium comes from hydrothermal fluids. Why sulfur doesn't come from the same hydrothermal fluids?
Yeah, actually, also a very good question, and I actually think they did. And the reason for that is that, so when we think about these hydrothermal systems, we're very sort of inclined to think of them in the same way as modern seafloor hydrothermal systems, and because we have such high sulfate in seawater, we cannot have them coexisting, because barite is so insoluble, so you need to have two different sources. But in the Archean, sulfate concentrations in seawater were 10,000 times lower than today. And if you then start to just do simple solubility calculations, you can actually have quite a bit of barium coexisting with it. And that means that, yes, you might have actually had both of them circulating through these systems and then just precipitating as a result of cooling, for example. However, we do know, the fact that we see this mass-independent signature in the sulfate means that it's not just leached, it's not only leached from igneous rocks, because we wouldn't see this atmospheric fingerprint. So yes, it might have circulated through the system. I actually think it probably did. But the rocks were not the main source of the sulfate.
Okay, so then if you look at, for example, carbonate deposits, even stromatolized, do you see the same sulfur isotopic signature or not, as the one that you assume comes from the atmosphere in the barite?
Sorry, can you say again?
Well,
I didn't hear this.
If the sulfur comes from the atmosphere, you should see it everywhere. So you should see it in barite, but you should also see it in gypsum, or you should see it in the sulfates that are present in the carbonates, like calcite and aragonite, that are formed in the stromatolites, for example.
Unfortunately, there are very little. There's basically almost no anhydrite from this time. It's not preserved. Carbonates are... okay, let me see if I can go back to that. So there is carbonate-associated sulfate, but not from the early Archean. But we do see... I have to go back more. We do see the same signature. Let's see. Here we go. So the green dots here is carbonate-associated sulfate. And this is, again, a little bit of an odd thing because the mass-independent signature switches compared to what we see in the barite.
Source.
Yeah, there is different explanations for this. So first of all, it's very difficult to measure carbonate-associated sulfate. So people have argued that there is maybe something in that is why we get a different signature. But we do know, I mean, in general, you can see when you go from the Paleoarchean to the Neoarchean that something changes. So this might be just a changing atmospheric chemistry. People have argued for things like organic hazes in the Mesoarchean. This is why we maybe have a more muted signal there, so then the UV radiation wouldn't penetrate all the way down to the troposphere. So I don't have a very good explanation for that, other than it is likely changing atmospheric reactions. So yeah.
And you don't have any gypsum deposits from the time? Not anhydrite, but gypsum?
No. I have literally just yesterday got data from tiny little anhydrite inclusions in nodules formed at sort of a beach at 3.2. This is all there is. But no, I think this is just, it's too soluble, I think, to be preserved, yeah. Or it's maybe too soluble to actually form if you have so little sulfate around.
And you don't find it in fluid inclusion? Somebody say on that.
Yeah, this is a good question. I don't know. At least nothing I know of that people have found. Yeah. Okay. But maybe we just haven't looked good enough. Thanks.
Thanks, Desiree, for the talk. Just wondering on the lines of continental crust, what do you indicate there? Like, do you mean like a widespread presence of the continent, like TTG kind of a crust? Or we know from the geologic record that it's mostly mafic at that time. So what are we hinting here? And if not the TTG context, then are we hinting at some localized crust, which could be giving you like a localized positioning of these barites in the context of this felsics?
Yeah, that is a question that is difficult to answer. But so first of all, I mean, we're not talking about the same amount of land as we have today, right? So we try to do some sort of back-of-the-envelope calculations of, okay, if you assume this weathering intensity, how much land would you need? And then you come, so today, 21% of Earth is land, 25. You get to something like between 2 and 10%. But this depends on how hard you assume that the weathering, or how intense you assume the weathering took place. If you have more intense weathering, you need smaller amounts of crust. So I think that, I mean, what exactly this was, I don't really know. What we can say is that to see this shift in strontium isotope ratio, it means that it must have actually been produced before 3.7, because otherwise you wouldn't have had ingrowth of your rubidium. So you must have already some reservoir that has formed a while ago, got this different strontium isotope composition, and then weather. So it's a bit of a question mark where this crust has gone to. But at least we know also from other isotope systems that seem to point at that crustal formation, felsic crust formed much earlier than what we have preserved in the rock record. So yeah, it's a bit of an open question. I don't know if that really answered your question, but at least I talked around it nicely, I think.
That's fair enough. Yeah, the other fold of the question is that we see all of that during the... So the question is again redirected towards the same line, but we see this presence of barite during the early Archean, but then you don't see it afterwards. And do you tie this up with silicification or processes like what you particularly have during the early Archean, not really going beyond early Archean and then into the Meso, and you don't see them again?
Yeah, this is a question that has been bothering me for a long time, and I haven't really answered. I mean, I can give you sort of the rough ideas that exist. One is that microbial sulfate reduction became so efficient that basically whatever little sulfate was around, that has been stripped out. Yeah, okay, possible. The other one is that hydrothermal activity reduced, so less barium, so therefore also no barite formed. Yeah, I don't know, also possible. We also came up with a very wild alternative hypothesis, is that these organic hazes would produce organic complexes with barium, and actually that is one way to dissolve barite or not crystallize barite. So organic molecules, organophosphate molecules can bound to barium, and then basically it would not precipitate, or it would form very tiny fine-grained barite that is maybe then not so well preserved. Again, this is, where we go into the arm-waving Archean geology. So I don't really know. Yeah, it's a puzzling question, and it's something we should find an answer to, because it probably tells us something about what happened to system Earth at this time. Maybe the third option is we're just not looking in the right places. So, yeah.
I have a question. You have your cartoon of how the environment may have looked like.
Yeah.
If you would have to put some scale there, where this hydrothermal activity would happen would be not like necessarily mid-ocean ridges.
No.
In present day, 2.5 kilometers.
Yeah, no, not at all. I think it must have been quite shallow. So, for example, this deposit, I mean, we find stuff like cross-bedded sandstones and things, and it looks like it was a fairly shallow setting. Actually, we find places where it looks like the barite has been eroded. So this must have, it seems to be fairly shallow, which also then is kind of intuitively makes sense if you think about this sulfate enrichment that you need to form them, or that the sulfur isotopes seem to point at. And this is much easier to do if you have some kind of shallowish, maybe like lagoon kind of basin. I don't know. Again, this gets very speculative, but I don't think I don't think this is deep marine hydrothermal. It's not mid-ocean ridge kind of style hydrothermalism. And it's also, again, it's relatively low temperature, probably some kind of diffuse venting. I mean, if we're now going to speculate, So, but then also you have to remember that the Archean there was probably much more hydrothermal activity just everywhere. So, yeah.
And maybe just a comment, we don't need to look for origin of life on Earth, as we just been announced that the asteroids can bring the goodies to Earth. So we have one more question, maybe.
Yeah, thanks, nice talk. I'm not a geochemist, but I'm interested to understand this weathering process. And you have calculated one time from when the weathering was started. So was this weathering a subaerial or a submarine? Because if it is a subaerial weathering, then it means the continental crust rose above the sea level, which is a very important point of Earth's history. So what is your take on that?
Yeah, so I think this was subaerial weathering. And this is for several reasons. First of all, submarine weathering is really much slower than subaerial weathering. So to get this effect of seeing the change, I mean, we're talking about changing the chemistry of the whole ocean. To do that, I mean, you need to have a fair bit of input. So I think submarine weathering would not be able to do that. The other thing is that it must be weathering of felsic material. And just from a physics sort of point of view, this is material that would likely be, this is produced higher up in topography because of the density of felsic crust. So if you have weathering of felsic material, I mean, yes, I will not say it's completely impossible that this happens on the seafloor, but it gets into sort of very unlikely scenario. It's much more likely that this was subaerial simply because that's where we have felsic material. Also, look at today's planet. This is where the felsic rocks are. We don't have ocean crust with felsic rocks. Mostly, not. So I think yes. So yes, I think it's subaerial weathering. But again, you have to remember that, yes, so I mean, this is why I argue for this. This means the emergence of land, but we're not talking about the amount of land that we have today, because if weathering was very intense, then small pieces of felsic crust being exposed can produce the same chemical effect on the oceans as weathering like we have today on a very large area.
With this, I would like to thank the speaker and invite you to thank her again by a round of applause. And Desiree will be at FAB until tomorrow after lunch, so please come by and try to find her to answer any other questions you may have. Thank you very much for being here.
Thanks.